So, we will come back again. So, before going to the example 6, just from the book I would like to show you that V string, right. When will this is your what you call, this is your V connection of the insulator. Look, this side one string, this is another string, and conductor is connected here. When we will study corona, I will show you the that corona, how things are happening. At that time also I will take from a book the photograph they have taken. At that time I will show you. So, this is your V string, and that your grading ring, right, whatever numericals we have done for grading ring also I am showing. Just hold on, before proceeding to the next example, just hold on. That different type of grading rings are there. Look, this is not photograph, but it is drawing actually. Look, the grading ring at the bottom of the string. Look, this grading ring is there. Here also look, different type of, this is also grading ring is there, right. So, this is how, if you look at the your what you call at that your transmission tower, you will find these things are there, right. This is just to show you that how things are. So, next we will come to the example 6. So, in a 6 unit suspension insulator string, the capacitance between each link pin and earth is 0.10 of the self capacitance of each unit. You have to determine the voltage across the lowest unit as a percentage of the total voltage and also the string efficiency, right. So, that is your problem. Now, we have already derived that we know that your V x upon V is equal to sin hyperbolic x root k divided by sin hyperbolic n root k. Now, for x is equal to n, V n is equal to V, therefore, we can write V n minus 1 upon V is equal to sin hyperbolic n minus 1 root k divided by sin hyperbolic n root k. Now, voltage across the lowest unit is given by small v n is equal to capital V n minus capital V n minus 1. So, you substitute that you V n is equal to V and V n minus 1 is equal to V into sin hyperbolic n minus 1 root k divided by sin hyperbolic n root k. Now, only you have to recall these formulas. Now, it is given that n is equal to 6. So, k is equal to 0.1. So, root over k is 0.3162. Therefore, sin hyperbolic n minus 1 into root k is equal to sin hyperbolic 5 root k. So, root k is equal to 0.3162. You multiply 5 into this one and then take sin hyperbolic of it, it will become 2.3273, right. And sin hyperbolic 6 root k, when n is equal to 6, it will become 3.2591. Therefore, small v n by capital V is equal to 1 minus sin hyperbolic 5 root k upon sin hyperbolic 6 root k. Substitute all these values, you will get V n upon V, that is 0.2859. N means that nth insulator, that that is the last one, last piece which is near to the conductor. So, that is small v n. So, it is 0.2859. Therefore, string efficiency will be capital V divided by n into small v n, but v n by V is equal to 0.2859. So, therefore, it is 1 upon 6 into 0.285, because if you take the reciprocal of it, it will be 1 upon n into V n upon capital V. V n upon capital V, small v n upon capital V is this one. Therefore, it is coming roughly around 58.29%, right. That is the string efficiency. So, next you will come to the selection of insulation. So, basically the insulation level, it affects the cost and reliability of high voltage considerably. So, normal operating and transient voltages are the primary consideration in selecting the insulation for a line, right. So, operating as well as transient voltage are the primary consideration, both you have to look in selecting the insulation for a line. So, that is transient over voltage, we will see those things later, right. The transient voltages include switching and lighting surges. So, when sufficient insulation is provided for switching and lighting surges, power frequency voltage requirements are satisfied, right. So, sufficient insulation will be provided by switching a lightning surges, particularly when you are designing everything, you have to take into account and accurate calculation is required. Next is the magnitude of switching surges is 2.5 to 3 times to normal voltage. So, that means the insulation should sustain that kind of high voltage, right. So, that is 2.5 to 3 times the normal voltage. That way you have to design. Next is that your switching surges assume greater importance above 230 kV insulation requirement. In our country 220 kV or above, right, 220 then 400 kV line. So, 220 kV 30 kV insulation requirements. Now, on the lines up to 230 kV, lightning is the major factor to decide the amount of insulation, because lightning stroke is very common phenomena in our country, everywhere all over the world, right. And you have to protect all these things. On the lightning is the major factor to decide the amount of insulation. If lightning stroke is there on the top of a tower, then you do not know how much it can affect to your equipments or apparatus at the substation. So, lot of protection is required. You have lightning arrestor and other things, but anyway. So, lightning is the major factor to decide the amount of insulation for everything. Then lightning insulation requirements depend on other factor also, like tower footing resistances, then number of your ground wires and conductor configuration etc. So, tower footing resistance, the number of ground wires, all these things are required, because grounding is another important factor. So, this lightning surges is very important phenomena in power system. And final choice of the number of insulators for a line is also dictated by the atmospheric conditions, then temperature and altitude of the place. So, many factors are associated that your what you call for number of insulators for a line. So, these are your like something like your general knowledge that we need all sort of things to know before making that your choice, choosing the correct insulator for a particular voltage level. Next is that atmospheric condition affect considerably the flashover voltages. It is very important, particularly for insulators. Wet conditions cause flashover at lower voltages also, particularly during rainy season, right. This can create problem. So, this flashover, I mean, I do not know whether you have observed or not, many times I have observed that flashover is happening, particularly during rainy season. Even in the railway traction line, any railway platform, sometimes you can observe that some flashover is going on. So, this I have seen somewhere that it is happening, right. So, dirty and wet surfaces of the insulator allow the leakage currents to flow over them, resulting in flashover. Naturally, if dirty and wet surfaces are there, so of the insulator, it will allow leakage currents, because it gets a conducting path, therefore, possibility of flashover is there, but it does not generally it does not spoil the insulator, right. Its insulator can withstand such kind of flashover. So, flashover voltage is proportional to the length of the leakage path, right. If I mean directly proportional to the length of the leakage path. Next one is that spacing of conductors. You have seen for transmission line 33 kV, 66 kV, 132 kV or 220 kV or above, you have seen different type of conductor spacings are there. Also in each phase you can see 2 conductors or 4 conductors are there in each phase. Recently I went somewhere, I found that 4 conductors are there in each phase, and you know why you use that 2 conductors or 4 conductors or even more for high tension transmission line, that why you use that. So, spacing of conductors. So, trouble service requires proper spacing of conductors. The conductor should be so spaced that corona loss is minimum. This corona loss we will see later, right. After this, after cable, first next we will cover cables. After cables, we will go to your what you call that transient over voltage and insulation coordination. After that, we will come to corona. So, that corona loss is minimum, and they do not clash your during swinging and vibration. That means, conductor spacing should be such that even during storm or wind, they should not your clash with each other, right. So, it should be, you have to see that the spacing of the conductors, you have to design accordingly, and those conductors when connected tower to tower through your insulation, you have to see the vibration will be less. So, there are many, no direct formula is there for conductor spacing, there is no direct formula, but some empirical formulas for conductor spacing S are given by the look. So many I have whatever I have got, I have brought it here. One is the spacing should be maybe 0.75 your root over delta plus v square by your this thing 2000, right. So, this actually will give some kind of ideas, right. So, that another is S is equal to 2 delta, then sin theta, then your what you call, another is S is equal to 0.65 root delta plus 0.007, another is S is equal to 0.75 root delta plus V upon 150. This way, so many your what you call so many this thing empirical formulas are there. So, when you design, they have to choose the proper spacing. This formula may serve as a guide to your calculate conductor spacing, temperature, ice and wind also affect the final choice. That ice, wind will see in sag and tension, right. During that sag and tensile calculation, we will see that your this your this thing what you call that this temperature, this ice and wind calculation. So, your consideration, this also affect the final choice. So, so many different logic is there, different empirical formulas are available, but no direct formula or proof, at least I have not got it anywhere. So, whatever I have got, these are the certain things, right. Now, here one question to you, that what is delta V you know and what is L, right. So, this is a question to you, I did not write for you, but and also 2 delta sin theta, everything has been taught, but before that. So, this is an exercise for you, right. So, you should find out. Then next is this is an exercise for you. I have not solved this problem, but I am giving it to you. When we will go through this video lecture, at that time we will do it. For example, a voltage V is applied across a string of N cap and pin type N cap and pin type insulator suspended from an earth cross arm of a tower. The capacitance between the cap and pin of each insulator is capital C, and the capacitance of each pin to earth is capital C0 suffix 0, so that the voltage across the insulator unit nearest to the line terminal is this. That means, V n, you have to find out small v suffix n is equal to V into sin hyperbolic n gamma minus sin hyperbolic n minus 1 into gamma divided by sin hyperbolic n gamma, where you have given something that sin hyperbolic gamma by 2 is equal to half root over capital C0 by C, C0 by C, this is given. So, based on that, you have to your what you call, you have to prove this, that small v n is equal to this one. So, with this, that I believe nothing is left for this thing cable chapters. So, sorry, insulator chapters. So, there are I mean whatever was there, varieties of insulators and other thing we have tried to cover, but whenever you have any questions or anything, you please put it into the forum or you can send mail to me, right. So, all these questions, other things will be clarified, and just this is mathematics is less in this chapter, theory is more, you have to learn different type of insulators and other thing, but this is insulators, cables, these are the main part of the power, main components of the power systems. So, in this course we will see, next we will see the cables. So, next let us come to cables, right. So, cable is a underground cable is a very big chapter, right. So, somehow I have tried to condense it as much as possible, particularly the number of diagrams and other thing, because I found in the literature that underground cables is it is not a small topic, it is a very big topic. So, somehow I have to restrict it compared to, because we have to cover many other things. So, first is introduction regarding underground cables. First thing is, you know, that general knowledge is that underground cable is much more expensive than your overhead conductor, at least 2.5 to 3 times more than that your overhead conductor. So, naturally cables are very expensive, but many places we use cables, particularly densely populated area or sometimes rural areas, and many places in hilly areas I have seen also cables are it is not like buried in the ground, but it is on the, you know, it is from pole to pole, it is cable has been taken. So, anyway, so different type of your cables are there. So, we will come for first little introduction, first 1 hour or so I think it will be theory only for underground cables. Some of the diagrams I will show, but all is not possible in this video lecture class, and somehow I have to condense this thing. So, first thing is, in densely populated areas large scale use of cable has been made for transmission and distribution of electrical energy. This is the first thing. So, cable consists of a central conductor. Later I will show you diagram and other thing. Central conductors with an insulation to isolate the conductors from each other and their surroundings. This is the thing. Cable have to have conductor, then insulation, sheet, so many things, armor, so many things will be there. So, external protection is provided for protecting against mechanical damage, chemical reactions and moisture etc., because cables most of the cases it will be buried in the ground. Therefore, you have to see there should not be mechanical damage and there should not be chemical reactions and moisture etc. So, it should not the external protection is required for the cable. The materials employed for conductor generally annealed copper or aluminum, either copper or aluminum conductor is used for the cables, right. So, diagram another thing I will show later, but all these things cannot be put it here, I have to condense. So, the use of copper, that use of copper is limited to cables used for control circuit, signaling and communication, right. So, as you know that your copper will be expensive than aluminum. Power cables use stranded or sector shaped aluminum conductors. I will show you the diagram later. Either it will be used stranded conductors, the way we have seen, no, the standard conductor like your one conductor, around the 6 conductor, then 12, then 18, those the standard conductors, or sometimes these sector shaped aluminum conductors are used. I will show you the diagram later. So, aluminum has a tendency to oxidize when exposed to air. So, we naturally have seen also aluminum has a that the tendency to oxidize, and they, because of this, that the oxide film forms a very high resistance. So, special jointing techniques are necessary, right, for this thing, for cable jointing. Suppose 2 cables are there, when you joint it, some special technique is required. So, some several jointing techniques such as soldering, welding and compression jointing are employed, right. So, this is the thing, but for cables you have to have insulations, you have to have insulation. Therefore, when we come to the insulation, right, the conductors of a cable have to be covered by an insulation to isolate the conductors from each other and from their surroundings. Suppose if you have a 3-phase line, then 3 core cables, then each one has to be insulated from each other, otherwise there will be short circuit, right. Therefore, insulation is more important. So, insulating material should have a high dielectric strength, high insulation resistance, good mechanical strength, and fourth one is to withstand temperatures from about -30 degree to over 100 degrees Celsius, right. So, these properties are required, and from the testing only you have to see that whether this property holds or not for the insulator, right. So, some properties of cable, some I mean these are the properties are required, main properties. So, typical some properties of cables are, look, this material is, one is XLP cable, then I will come to that most of the cables later, then polyethylene your thermoplastic, then ethylene propylene, that is rubber, then butyl rubber, then PVC, then oil impregnated paper, right. So, different type of insulation, the typical properties of cable, right. So, dielectric strength for this one kilovolt per millimeter is given. So, XLP is 18, many places XLP is used mostly, right. Then 21, then 15, 13, 20, 17 and 21. So, dielectric strength among all these maximum is that polyethylene thermoplastic one, right. Therefore, your permittivity 2.5, 2.3, XLP is 2.5, then ethylene propylene 2.8 and butyl rubber 3.2 and oil impregnated paper highest is 3.0. PVC is the highest 5 and oil impregnated paper is 3.6. Now, temperature rating, one is maximum continuous, one is short time overload, another is short circuit. So, I mean 90, if you look at that 90 here, then 75, 90, 85, 75, 80 more or less, except polyethylene, your polyethylene, thermoplastic and PVC more or less all are 80, 90, the maximum continuous temperature. That means, that is your what you call temperature rating. Maximum continuous means at normal operating condition it can withstand this continuous temperature. Now, short time overload, if there is an overload, right, for say for a very short time, then XLP is 130 and next your ethylene propylene, the rubber 130, then others are there 110, that oil impregnated paper, then PVC 95 and so on, all these things. Then short circuit, it is 250 and this ethylene propylene is 250, others are 200 or 150, that is during short circuit the temperature rating. Short circuit last your what to not for longer duration, right. So, this is your typical properties of cable insulators. So, different type of insulators are there. Next one is that VIR cable, this is vulcanized India rubber we call, it was developed in 1870, that is more nearly 147 years ago, but at that time anyway those days there was no electricity in those days, right. It came later, but anyway this vulcanized rubber was used, I mean developed in 1870 and has a dielectric strength of about 10 to 20 kilovolt per millimeter. When I am putting this thing because 1870, so just putting a question to you, when the first, of course not high voltage or I cannot say high voltage, but first transmission system or power transmission system, when in which year it was started and which place, this is a quiz to you, right. So, you this is a quiz to you, so you should find out, and has a dielectric strength of about 10 to 20 kilovolt per millimeter and the dielectric constant is about 2.5. In this case it is a vulcanized rubber, so sulfur actually mainly used as the vulcanizing agent. So, this insulation is limited to wiring cables for lighting and minor power installation, that means at low voltage level this type of cable can be used because it is for lighting and minor power installation. Next one is that elastomer insulated cables, right. So, these are all coming from polymers. So, elastomeric insulation includes rubber, butyl rubber, silicon rubber and ethylene propylene rubber, right. So, different type of, if you if you see those cables, I mean in your, then you will see different type of insulations are used. So, of course, it depends from your different properties as well as cost is another important aspect. So, since natural rubber can be used only up to an operating temperature of 60 degrees Celsius. So, considerable effort has been devoted to the development of synthetic elastomeric compounds with superior properties such that its operating temperature can be increased. So, details we will just condense it. These are all these thing different insulation. For example, polyvinyl chloride cables, that PVC cables they call polyvinyl chloride is a synthetic material obtained from acetylene and can be produced in a number of grades depending on the polymerization process used, right. PVC cables also used. So, it is the form of a white powder. The advantage is which is odorless, tasteless, chemically inert, non-inflammable and insoluble. at ordinary temperature in all liquids. This is the major advantage is that it is chemically inert, non-inflammable and insoluble at ordinary temperature in all liquids. This is actually this is the main advantage of this one, right. So, this is your what you call that PVC cable diagram, other thing construction I will come later. Then is in pure form it is rigid and brittle at low temperature, right. In pure form it is rigid and brittle at low temperature. I have seen somewhere the cables, low tension cables, that cable was for nearly, if I recall correctly, the people told me nearly 25 to 30 years supplying power. Cable is without any fault or anything. When they were trying to replace it, and I saw it in my eyes that when they were trying to replace those cable, you know, it was I mean it was not in its original conditions. So, it became very brittle, right, and everything is very loose, but as long as it was in your under the ground or this that there was no problem at all. So, anyway, people, I mean those they have told me, I have seen this one. So, when used for cable insulation, it must be combined with a plasticizer whose function is to form a gel and the material plastic over the desired range of temperature, right. Its mechanical properties are not as good as those of rubber, and the insulation resistance is also lower than that of rubber. Insulation resistance is a great matter for cables, right. So, however, it is inert to oxygen and almost inert to oils, that means there will be no reaction, and many acids and alkalis your alkalis also, right. So, this is the advantage, therefore, it is preferable to rubber in many environmental conditions. So, you have to consider many things, which environment you are using the cables, and accordingly you have to choose, right. Then is next one is the polythene insulated cables. So, polythene is a straight chain polymer derived from ethylene. So, its electrical properties are very good. Number one is very low power factor at all frequencies, low dielectric constant and high resistivity, right. This is your polythene insulated cables. It has a limited application as a power cable in your power cable insulant. However, a 3 core 11 kV self supporting aerial cable which can be used for rural distribution. Aerial cable means not buried in the ground, you can take it through the tower or you know or some kind of arrangement, right. Due to its low weight, it can be suspended from the existing low voltage poles. That is why low voltage pole also you can make it. I have seen somewhere, I mean I do not know nowadays, it may not be there, but in hilly areas I have seen this aerial cable. Even it I saw that it is going through your trees instead of pole, because many trees are there. So, it was going, I have seen it in the past. So, next one is that XLP cables, that is cross links polythene cables, XLP cables, right. So, it has a low density polythene when vulcanized under controlled conditions results in cross linking of carbon atoms and produces cross linked polythene. This is mostly that chemistry portion. So, we will not cover that, but some general ideas, right. This new material does not melt, but carbonizes at 250 to 300 degrees Celsius and has become very popular as insulating material, right. So, XLP cables possess the advantages of lightweight, then small overall cable dimensions, low dielectric constant and good mechanical strength. So, it has some properties that your what you call which it can be preferable to compared to other cables, right. So, that means these cables permit conductor temperatures of 90 degree Celsius and 250 degree Celsius under normal and short circuit conditions respectively. So, 90 degree normal is quite high, and at short circuit 250 also it is okay, and can be buried directly in soil as this inclusion as this insulation has low water absorption. So, that means without anything you just can your what you call you directly lay in the soil. You might have seen the cable laying when how they are doing it, right. So, these cables have been found to be very suitable for all voltages up to 33 kV, right. So, thank you very much, again we will back.